The 19th century marked a turning point in our understanding of disease. It was a time of great scientific curiosity and groundbreaking discoveries that would forever change the landscape of medicine. Before this era, illness was often attributed to miasmas or bad air. This belief was deeply rooted in ancient medical traditions and persisted for centuries. However, pioneering scientists like Louis Pasteur and Robert Koch challenged this notion. They embarked on meticulous research and experiments that would eventually debunk the miasma theory. They championed the germ theory of disease, a revolutionary idea at the time. This theory posited that microscopic organisms, rather than foul odours, were the true culprits behind many illnesses. It was a radical shift in thinking that required substantial evidence to gain acceptance. Pasteur, a French chemist, is renowned for his work on pasteurization. His experiments demonstrated that heating liquids could kill harmful microbes, preventing spoilage and disease. This process, which kills microbes through heat, revolutionized food safety. It had a profound impact on the dairy and wine industries, ensuring that products were safe for consumption. He also developed vaccines for rabies and anthrax, showcasing the potential of immunization to prevent deadly diseases. These breakthroughs solidified the germ theory's place in scientific thought. The medical community began to embrace the idea that germs were the root cause of many diseases. Meanwhile, in Germany, Robert Koch made groundbreaking discoveries in bacteriology. His meticulous methods and innovative techniques set new standards for scientific research. He identified the bacteria responsible for tuberculosis and cholera, two of the most devastating diseases of the time. Koch's work, along with Pasteur's, provided concrete evidence that germs were indeed the cause of many diseases. Their findings were instrumental in shifting the medical paradigm. These discoveries laid the groundwork for a new era of medical research. Laboratories around the world began to focus on identifying and studying pathogens. Scientists began to hunt for the microscopic agents responsible for a wide range of illnesses. This quest led to the discovery of numerous bacteria and eventually viruses. This shift in understanding had profound implications for public health. It led to improved sanitation practices, which significantly reduced the spread of infectious diseases. It paved the way for the development of life-saving vaccines, which have since eradicated or controlled many deadly diseases. The stage was set for a deeper exploration of the microbial world, including the elusive viruses. This new frontier promised to unlock even more secrets of the microscopic universe, leading to further advancements in medicine and public health. In 1889, a new and deadly respiratory illness emerged in Central Asia. This illness, which would later be known as the Russian flu, began its journey in the bustling towns and cities of the region, where people lived in close quarters and trade routes were busy with activity. It quickly spread across the globe, becoming the first true pandemic of the modern era. The interconnectedness of the world through trade and travel facilitated the rapid transmission of the disease, reaching distant continents in a matter of months. This pandemic, dubbed the Russian flu, left millions infected and thousands dead in its wake. Hospitals were overwhelmed with patients, and the medical community struggled to provide adequate care with the limited knowledge and resources available at the time. At the time, the germ theory was still in its infancy. The understanding of how diseases spread and the role of microorganisms was a relatively new concept, and many scientists were just beginning to explore this uncharted territory. Scientists were ill-equipped to identify the causative agent of this mysterious new disease. The tools and techniques they had were rudimentary, and the process of isolating and identifying pathogens was fraught with challenges and uncertainties. Enter Richard Pfeiffer, a German bacteriologist who believed he had found the culprit. Pfeiffer was a prominent figure in the field of bacteriology, and his work was highly regarded by his peers. He isolated a bacterium now known as Haemophilus influenzae from the sputum of infected patients. This discovery was seen as a significant breakthrough, and many hoped it would lead to a better understanding of the disease and how to combat it. Pfeiffer proclaimed this bacterium to be the cause of influenza. His announcement was met with a mix of excitement and skepticism. as the scientific community debated the validity of his findings. His findings were met with both excitement and skepticism within the scientific community. Some scientists were eager to accept his conclusions, while others questioned the evidence and called for further research. The identification of H. influenzae as the cause of the Russian flu was a mistake. Later research would reveal that influenza is actually caused by a virus, not a bacterium, highlighting the limitations of the scientific knowledge and techniques of the time. However, it highlights the challenges faced by early scientists grappling with infectious diseases. The quest to understand and combat these illnesses was a daunting task, and many early researchers made significant contributions despite the obstacles they faced. The tools and techniques available at the time were limited. Microscopes were less advanced, and the methods for culturing and studying microorganisms were still being developed. This made it difficult to isolate and identify the true causative agents of diseases, especially viruses. The discovery of viruses would come later, revolutionizing the field of microbiology and leading to more accurate diagnoses and treatments. The Russian flu pandemic, despite its mysterious origins, served as a stark reminder of the devastating potential of infectious diseases. The widespread suffering and loss underscored the importance of scientific research and preparedness in the face of such threats. It underscored the need for continued research into the causes of these illnesses. The lessons learned from the Russian flu would pave the way for future advancements in the understanding and treatment of infectious diseases. The scientific community was now on high alert, ready to confront the next emerging threat. The experience of the Russian flu pandemic galvanized researchers and public health officials to improve their methods and collaborate more effectively in the fight against infectious diseases. While the world grappled with the devastating Russian flu, another deadly disease silently plagued humanity: yellow fever. This mosquito-borne illness ravaged tropical regions, claiming countless lives and causing widespread panic and suffering. In 1900, a determined U.S. Army physician named Walter Reed led a courageous team of researchers to Cuba. Their mission was clear and urgent: to unravel the mysteries of yellow fever and find a way to stop its deadly spread. At the time, the prevailing theory was that yellow fever was spread through contact with contaminated clothing or bodily fluids, a belief that guided public health practices. However, Reed, with his keen scientific insight, suspected a different and more elusive culprit: mosquitoes. To test his groundbreaking hypothesis, Reed and his team conducted a series of daring and meticulously planned experiments. They allowed mosquitoes to feed on infected patients, then on healthy volunteers. The results were nothing short of groundbreaking and revolutionary. Reed's team demonstrated conclusively that yellow fever was transmitted through the bite of infected mosquitoes, a discovery that changed the course of medical history. This monumental discovery revolutionized our understanding of disease transmission and the role of vectors in spreading illness. It also highlighted the critical role of vectors such as insects in the spread of many other diseases, prompting new approaches to public health. Reed's work had far-reaching implications, influencing public health policies and practices around the world. It led to the development of comprehensive mosquito control programs that dramatically reduced the incidence of yellow fever and saved countless lives. Perhaps more importantly, his meticulous research paved the way for the discovery of viruses, a new frontier in medical science. Yellow fever, it turned out, was caused not by a bacterium but by a virus, a microscopic agent even smaller than bacteria, opening up a whole new world of scientific exploration and understanding. Section 4. The Spanish Flu, a Global Tragedy, Ignites Scientific Inquiry. In 1918, as World War I raged across Europe, a new and terrifying enemy emerged: the Spanish flu. This influenza pandemic swept across the globe with unprecedented speed and ferocity, infecting an estimated 500 million people and killing between 50 and 100 million. The world had never seen anything like it. The Spanish flu pandemic was a wake-up call for the scientific community. The sheer scale of the tragedy underscored the urgent need to understand and combat influenza. Scientists around the world raced to identify the causative agent, develop treatments, and prevent future outbreaks. However, the tools and knowledge available at the time were limited. Researchers struggled to isolate and identify the virus responsible for the pandemic. The electron microscope, which would later revolutionize virology, was still decades away. Despite these challenges, the Spanish flu pandemic spurred significant advances in influenza research. It led to the development of new techniques for studying viruses and the establishment of research institutions dedicated to influenza. The world was now acutely aware of the threat posed by this deadly virus. Section 5. Richard Shope's breakthrough, unveiling the link between animal and human influenza. In the 1930s, a young American virologist named Richard Shope made a groundbreaking discovery that would forever change our understanding of influenza. Working at the Rockefeller Institute for Medical Research, Shope turned his attention to a respiratory illness affecting pigs, swine influenza. Shope suspected that swine influenza might be caused by a virus. He set out to isolate and identify the culprit. Through a series of meticulous experiments, Shope succeeded in isolating the swine influenza virus. He then demonstrated that this virus could infect not only pigs but also ferrets, a common laboratory animal. Shope's discovery had profound implications. It provided the first evidence that influenza viruses could cross species barriers. This finding suggested that animal influenza viruses could potentially infect humans, a concept that would later prove critical to our understanding of pandemic influenza. Shope's work laid the foundation for future research into the animal origins of human influenza viruses. It also highlighted the interconnectedness of animal and human health, a concept that remains central to the field of emerging infectious diseases.